assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
This question says that carbon monoxide and chlorine gas react to form phosgene. It gives us the reaction, and then it gives us the equilibrium constant with respect to pressure, or Kp. It says it's 3.1. And then it asks, if a reaction mixture initially contains 215 torr of CO and 245 torr of Cl2, what is the mole fraction of CoCl2 when equilibrium is reached? The first and most important thing to remember in this question is that the equilibrium constant with respect to pressure Kp is almost always written in terms of atmosphere or bar, not in torr. If you do this in torr, you would get the wrong answer. So the first step would be converting each of those partial pressures from torr to atmosphere, and you simply do that by dividing them by 760. So 215 divided by 760 is 0.28829. And everything from here on out is in atmospheres. I'm not going to write it out to save space. And if you divide 245 by 760, you would get 0.3224. And again, that's in atmospheres, which you need to do if you're going to use this equilibrium constant with respect to pressure. And there is no Cl2 to begin with. So we can complete our ice table. These were the initials. We're going to write the change, and then we're going to write the equilibrium. The stoichiometry of this reaction is 1 to 1 to 1, which makes this easy. We're going to lose some amount of each of the reactants and gain the same amount of product. So then an equation to represent the equilibrium partial pressure would be the initial, 0.2829, minus the change. Same for Cl2, the initial minus the change, and the final, or the product, CoCl2, would just be X, the initial plus the change. So these are the equations that represent the partial pressures at equilibrium for each of these gases. We can plug these into this equation for the equilibrium constant. That's the partial pressure of the products, CoCl2, divided by the partial pressure of CO multiplied by the partial pressure of Cl2. And so Kp equals X divided by 0.2829 minus X multiplied by 0.3224 minus X. And that again equals what it told us at the beginning, 3.1. If you rearrange your terms to get the quadratic formula, you would find that it is 3.1x squared minus 2.87643x plus 0.2827 equals 0. And if you solve your quadratic, you would find that x equals 0.1117. With this value, we could then solve each of these equations here. If you plug x into each of the three spaces, you would get 0.1712. I am going to write atmospheres here to remind us. And you would get 0.2107 atmospheres. And just x, 0.1117 atmospheres. Great, but it asks for the mole fraction. And so that is equal to The symbol there is chi, which is kind of this big X. That is equal to the number of moles of COCl2 over the total number of moles. And we have pressures, but we don't have moles. But fortunately, if you look at your ideal gas law, PV equals nRT, that's how I think of it. If you were to convert each of these from pressure to moles, the volume, the gas constant, and the temperature are the same for all of those conversions. So we can just use atmospheres as a proxy for moles. They're proportional in this situation. So instead of converting each of these to moles and then finding the mole fraction, we can just use these as stand-in for the moles. So we can do the partial pressure of COCl2 divided by the total pressure. And if you sum these three terms together, you would get 0.4936, and then you would get a mole fraction of 0.226. And this is the mole fraction of COCl2.